All right, let's share the screen. Check for recording. We are recording. Fantastic. All right, let's get started. This is chapter 14 for the Geology class at Gilbert Community College. We will be discussing groundwater today. So, when I say groundwater, you probably already have an idea of what I'm talking about. It is the water in the ground. More specifically, it is the water found in the pores of soil, sediment, and fractures of bedrock. So groundwater isn't like a lake of water necessarily, it's the moisture within the water. You dig into the soil, you get that really wet, damp soil. That's groundwater. It is the largest reservoir of fresh water available to humans. That being said, it only makes up about 0.6% of the hydrosphere. Because as we talked earlier, the majority of water on the earth is salt water. And then a very few amount of that is fresh water. And groundwater itself is a small portion of that, about 14.6%. And then, of course, your lakes and rivers and stuff like that are even a tinier percentage on top of that. Groundwater is used in many, many different ways. The sources of freshwater in the U.S. consist about 77% surface water and 23% groundwater for use. There obviously is more groundwater in the U.S. than surface water, but we tend to use a lot of surface water. Within the groundwater conversation, the vast majority of groundwater use is for irrigation. Public supply cuts in about another 20%, and then everything else is almost minuscule by comparison. Surface water does a lot of work for a lot of these things. Here in Houghton, where we have the where a lot of you are taking this class from, about 100% of our actual water for use comes from groundwater. We don't actually suck from like Lake Superior and stuff like that. Groundwater is, of course, very important in a geologic sense. Groundwater acts as an erosional agent by dissolving and removing soluble bedrock, such as limestone, right? We've talked about limestone, how it boils off when it gets in contact with water. Groundwater touches it, it boils off, producing things like we have here, right? Most water underground comes from precipitation or snowmelt, if you will, that soaks in or infiltrates the ground. So where does the rain go? It goes into the ground, right? What's the water in the ground called? Groundwater. Makes sense. Maybe a part of soil moisture, which I've talked about before, which you use for plants and tends to evaporate directly back in the atmosphere. As shown here, we talked about this a bit when we talked about soils. You do have an unsaturated zone, however, that includes the water in the air, but it's not really considered groundwater. Then you have your zone of saturation down further below, which would be your groundwater section. So the water will sink through the unsaturated zone until it hits the capillary fringe, the water table level, if you will. And then you get into technically what's called groundwater. So the groundwater is the water that doesn't necessarily go anywhere, if you will. The unsaturated zone is moist, as I said previously. But when a engineer says groundwater, he's talking about something technically different. Here you have your zone of saturation, the zone in which all pore spaces are completely filled with water, hence your groundwater. So water exists in the unsaturated and the saturated zones. However, the water table starts at the zone of saturation where you have complete infill of water within the pores. The water table, you've heard that phrase countlessly before, I'm sure. It has a depth that is highly variable. It's variable on a seasonal level, if you will. Precipitation variations affect the depth of the water table, and it also varies on shape. It is somewhat of a subdued replica of surface topography, so a valley would tend to also be a dip in the ground in the water table. A hill will be a raise in the water table. We've talked about this previously, but water tables. Actually, have we talked about this? I don't know if we talked about this previously. Water tables are a direct result of rainfall, so much so that if you have a steady drop in water level from May and November, this is the result of water discharging from aquifers to feed springs and systems, but not being replaced by recharge. And then in November, January, April, these things recharge, as shown on this chart here. Why is it recharging at these points? Well, precipitation, right? You don't have necessarily as much precipitation in certain times of the month, so you have a discharge of the groundwater levels, and then when it rains more and you have more precipitation and your snow melts, you refill those water tables up. Is the idea, is the argument we try to make here. Groundwater is, of course, connected to streams. There's gaining streams, which, of course, receive water from groundwater, and the water table this is done because the water table is higher than the stream itself. So as you can see in this image down below, the stream sucks in the water from the standing water table. As opposed, of course, to a losing stream, well, the water table is lower than the stream, and the water table sucks water out of the stream. Again, they're showing this image down below. This stuff's kind of obvious, I would imagine, to most people. Losing streams can, of course, be disconnected, wherein the bottom of the stream is not even touching the water table, as shown here, creating a bulge, if you will, at the water table, because the water in the stream will go through the soil down and then be spread out once it hits the water table itself. Let's talk factors that influence the storage movement of groundwater. The first and biggest would be, of course, porosity, or the pores, the open spaces in the rock and the sediment. This porosity is determined by the size and shape of the grains, the sorting of the grains, the packing of the grains, things of that nature. And you got to think there's got to be a space for the water to sit. If there's no place for the water to sit, the water is not going to sit there, right? If grains are very tightly packed, there's no space between the grains for water. Therefore, you do not have good porosity. Therefore, you do not have lots of groundwater. These two examples here on the left, the beaker is filled with 1,000 milliliters of sediment. The beaker on the right is filled with 1,000 milliliters of water. The sediment-filled beaker can contain 500 milliliters of water and still essentially be at the same level because the pore spaces are now filled with water. So the amount of sediment didn't change, but it soaked up all that water because all that space in between that was air is now water. Permeability would be a factor in groundwater storage movement, or the ability of a material to transmit fluid. This depends on the connectivity between the pores, essentially. How you got all these little spaces and holes in your soil, in your ground. How well are they connected? Are they all very separated from each other? Is there low permeability? Are they poorly sorted or tightly packed, perhaps? Well, then groundwater can't get between those spaces quite as well. This thing such as clay, very, very stupidly low permeability, we call that an aquitard, an impermeable layer that hinders or prevents water movement. And then naturally and as opposed to aquitard, you have aquifers, which are highly permeable rock strata or sediment that transmit groundwater very freely. Sands and gravels would be an example of this. In general, groundwater moves super, super slowly, about 4 centimeters per day. And a simple groundwater flow system uses the force of gravity and pressure differences to move the groundwater around. Groundwater tends to replenish in recharge areas and flows back to the surface in discharge areas such as streams or springs. In essence, what I'm saying here is there's no mechanism besides nature to move groundwater around. Groundwater is going to fall because of gravity. Groundwater is going to move because of pressure differentials. And all that depends on the soil that is holding the groundwater, its permeability, and its porosity levels. Simple groundwater flow system shown here, wherein you have recharge areas in the hills. The hills get saturated with water. The water comes down, and eventually it flows into those rivers, into those discharge areas up top. Notice the water level is bending up with the hill and down with the valley. Here's an equation for groundwater movement, Darcy's law. Don't worry too hard. It looks complicated. It's really not. And essentially, how conductive or permeable is the soil? How big is the soil? And how steep is the difference between the water table and where it's trying to go? If you have a very steep hydraulic gradient. There we go. A very steep hydraulic gradient. Water flows faster. Area is very large. You're going to use more water to move, things of that nature. May look like a complicated equation. I promise you it's not. See, here's what I'm telling you. You know, hydrologic gradient. You got a couple wells in here show that tap the water table at H1 and H2 height. The difference between those and the distance it travels gives you that denominator in, sorry, that denominator, that third part of Darcy's law. And it also tells you how fast the water is going to move in this water table hill here. You can map this stuff, obviously. If you have all the information, you can map water table levels. And what's these little dots here, these little blue circles, would be wells that essentially verify these laws. Yeah, shows you how groundwater moves, where it moves to, where it moves from, zones of saturation, zones of discharge, etc., etc. Hypothetical groundwater flow system shown here. Aquatods inhibiting motion. The water table itself, the groundwater itself, is considered a uniform aquifer for this example. And we can see that we have zones of discharge in high level areas, such as these hills. Zones of discharge. I forgot the word already. Geez. Recharge, there we go. Zones of recharge in the hills, right above the water table. Zones of discharge in the lakes and streams. And then we have subregional movement, pressure movements essentially in the red arrows, bringing water out from the groundwater into the river, stream, and lake environments. And then down there, the black arrows, the deep regional systems, more so gravity defined with a little bit of momentum and pressure differences as well, skipping around those aquatod units. So take a second, if you want, pause the video, take a good look at this, try to figure out where all these arrows are coming from, why all these arrows look the way they look. Why, for example, are all the red arrows moving more or less in the same direction, where the blue arrows tend to not. So again, pause the video if you want, take a look at that. So we talked before about those blue dots being wells in the map. Here's wells. A well is essentially a hole bored into the zone of saturation. You can have drawdown at these locations as the water is withdrawn from the wells. Surrounding water table is, of course, lowered. Anyone who has a well system at their house will know water table can be a factor you need to consider. And, of course, you have a cone of depression where you're actually sucking the water out. A cone forms as you suck water more from the well than from the surrounding water table. Here's those cones, cone depression shown here. And yeah, this affects directly the pumping. Notice here, the well used for irrigation is pumped. So a cone depression occurs when you use it heavily, and those dry wells on the left and the right actually do not get access to that water anymore because the irrigation is producing a cone depression, sucking all the water in down to its tip down there. You have perched water tables. This would be where you have an aquatod that is essentially perching water on top of it, as shown on the left of this image here. And natural springs can occur as a result of these perched water tables. That's how you can get water like this. This water is flowing out of a perched water table. It is feeding the lake there, though, and what that means is that the water table itself is higher than this lake is. Artesian well, I'm sure you've heard that before, a spring is groundwater that's under pressure and rises above the level of the aquifer. The water needs to be on an incline confined. The water must be in an incline confined aquifer for these to happen, and aquatods need to exist above and below. Keep in mind the aquifer confining, essentially building that pressure. Shown here, you have an example that can give you an artesian well. 1 and 2 down there in the image are non-flowing and flowing wells. And what happens here is you notice you have that brown rock layer is an aquitard. It's not allowing the water to move up and down. Instead, it has to flow along laterally from the recharge area. Since that is happening, you have all this pressure showing, and way down there at 2, a flowing artesian well happens where the water finally has a spot for it to come out. It pimples itself out, if you will, and shoots out as a flowing artesian well. Flowing and non-flowing, I discussed this already. There it is in text for you. And yeah, they're very nice. And a municipal water tower is essentially an artificial artesian well system, wherein water is pumped into the tank, and then the tank holds the pressure necessary such that the water flows out of the tank and gives you the pressure required to move the water through the pipes and feed your houses. Waters could be hot springs. If the water from the well is next to a heat source, usually igneous in nature, magmatic in nature, you can get hot water. You can get hot springs. If you've ever been to one, they're fantastic. Highly suggested. Geysers, again, same song and dance. Essentially, this is an intermittent hot spring where there comes the hot air eruptive force. Old Faithful, of course, the world's most famous geyser, if you ever get to Yellowstone. And they happen kind of how you would imagine. You have this water, this trapped water in some sort of cavern or aquifer system that's surrounded by aquitards. As the heat flows up, that water gets hotter and hotter. Water, when it gets hot, turns into steam, expands, shoots up. Problems associated with groundwater. Mining would be an example of this. Mining occurs when the recharge is significantly less than the removal. Essentially, you are using this water to help your mining. You're drawing out water way faster than it can be replaced naturally. Here we have some examples of some high plains aquifers. Because of the high porosity, excellent permeability, and great size, the high plains aquifer is the largest in the United States and accumulates enough fresh water to essentially fill Lake Huron. That being said, that during the past 60 or so years, water and storage of the high plains aquifers declined by about 200 million acre feet, or 65 trillion gallons. A 62% decline occurring in Texas necessarily. See that red arrow down there below, the decline? And what's happening here is this aquifer is being used by people with access to it so hard, it's not refilling naturally from these rivers, rain, snowfall, etc. And it's essentially depleting in certain areas. Irrigation, of course, would be very common. You've driven past farms, you've seen them irrigating those gigantic sprinklers irrigating those crops. Water simply does not refill fast enough for us. When you have lots of use of groundwater and not refilling it, you can get subsidence, where in the ground itself sinks because the water is not there to hold it up anymore. The San Joaquin Valley in California would be an example of this ridiculous picture. This nice old man here on the right shows how much the land itself has changed due to the groundwater being pumped out. It is an amazing, amazing amount. Example here, again, subsidence area wherein the groundwater is pumped out and it collapsed. Saltwater contamination can be an issue. Excessive groundwater withdrawal can cause the salt water to be drawn into the wells. A pressure differential can cause salt water to be drawn in, contaminating the fresh water. You don't want to drink salt water. I think we're very much all aware of this. Mainly a problem at coastal areas, necessarily. As shown here, you're next to the ocean, but you're far enough away that your well hits fresh water, but you get that cone forming when you pump the water so hard that the groundwater that is salty from the ocean will actually impede into the fresh water, and your well will start, chronic depression, there we go, your well will start drinking up the groundwater, essentially making it useless to you. On the same note, you can get groundwater contamination from, say, sewage or garbage, and it basically follows the same idea. Septic tank would be an example here, wherein the water from your garbage, your sewage, your septic tank will flow, eventually touch the groundwater. And if it does it at a high enough pace, then you can actually get contaminated water from this event. It's the same base concept as the saltwater contamination, just the source is different. So I don't think I need to go too deep into it. And it can be a lot worse naturally. Fertilizers, pesticides, industrial materials, what have you, can infect groundwater if you don't properly adjust your use of it. Groundwater dissolves rock. Talked about this earlier. Most groundwater is mildly acidic. You know, your 7 on your pH scale comes from distilled pure water, not necessarily groundwater. Most of your groundwater contains carbonic acid. This is why well water tastes different, right? Carbonic acid, for example, reacts with calcite in limestone to form calcium bicarbonate. We talked about this already. Dissolves limestone, forming caves. About 17,000 caves alone in the U.S. have been discovered, and most of them come from acidic groundwater dissolving soluble rock. Very common. Dripstone depositions can form. Calcium carbonate deposited as dripping water evaporates, and it's called travertine. And yeah, stalactites and stalagmites form from this groundwater drippage, as shown here. If you've ever been to a cave with stalactites and stalagmites, you know they're super cool. How they form, that's water slowly dripping off from the cave. Where's that water coming from? Well, it's the groundwater that's coming from there. Karst topography is a interesting issue you can have with groundwater. This is the landscape is shaped by the dissolving power of groundwater. Commonly features sinkholes and is due to a lack of surface drainage or streams. The streams flowing through the caves underground rather than on the surface. Here's some example of some karst topography. And these are sinkholes, again, caused by this destruction of the underlying soil, the underlying groundwater. And as the water table sinks down, the areas that were once filled, let's say a limestone, is dissolved away. That falls in, giving you sinkholes, sinking streams, solution valleys, things of that nature. If you want to take a second pause, look at this video longer if you don't understand this process. Costs are not uncommon if you have limestone under the ground and you have somewhat acidic groundwater, which is a lot of it, you're going to get these things happening. Your carbonates, your evaporates, things of that nature. They're, as I said, they're not uncommon, these sort of topographic features. As usual, we got questions. I got a bit more to cover after these questions, so stay tuned for a bit. I'm still going to walk through these slowly. If you want to pause, try to answer the video, try to answer these questions in the video. It's only going to help you when you go on to your assignment and things of that nature. But we'll just roll through these guys. Again, I'm giving you time to pause. What is permeability? You should know that. It's a good thing to know. Makes best aquifers. Describe an artesian well. That's going to be something kind of useful. All right. So, water use. We talked about groundwater. We said groundwater is a lot of the use of a lot of the water that humans use is from the ground. Textbook says that the average American uses about 70 gallons of water each day. The U.S. differs in that, 80 to 100. And the average African in those less developed countries uses about 5. Big difference, right? But 1.1 billion on Earth do not have access to safe drinking water. That's not a good thing. So let's talk this groundwater usage. So according to the EPA, the average American family of 4 uses 300 gallons of water per day at home. 70% of that's indoor, 30% is outdoor, but obviously these numbers can vary. 300 gallons per day. That's not just the water you drink, it's everything, right? Where do we use our water? Well, the majority of it's actually in our toilets. If you don't have a high efficiency toilet, this is probably actually more. So actually this is 99, so this would be low efficiency toilets. High efficiency toilets use less, but every time you flush your toilet, there's a lot of water moving. You may not realize that, but that tank on the back is pretty full of water, and all that drains out with each flush. Wash your clothes, lots of water from washing your clothes. Shower, lots of water using your shower. The amount of water use each day is pretty amazing. What do you do and use the water? Well, you remove the water from the source. Usually you want to use it and put it back to where it came from. This is the water systems most of us have, but it's not a one-to-one, and it's not always super efficient. You can also not put the water back, such as irrigation, and technically the water does go down, but plants use up a lot of it, so not quite as well. Here are some industrial water uses in the U.S. Some of these are water users, not water consumers. Some of this water does get filtered back, but not really. So we can look at these examples. A kilogram of steel takes about 220 liters of water. That's a lot of water, right? Kilogram of paper, 4 times that much. Pretty ridiculous, right? Oh, you just wait. A single car, on average, uses about 400,000 liters of water in its production. And not all that water cycles back, by the way. We use a lot of water in the industrialization of our economy, of our technology. A single kilogram of ground beef, for example, uses about 7,000 liters of water. Remember, that is water consumption, not water use. So that 7,000 liters per kilogram of beef is done. That's about 2.2 pounds there. So that is 2 of those little tubes you get from like Walmart or something like that. 2 of those tubes cost humanity 7,000 liters of water. It's pretty ridiculous. But that's how the economy is functioning currently, right? So let's use Bob as an example. Bob uses 100 gallons of water that comes out of the faucet each day as his everyday activities. Is that the end of the conversation? No, not really, right? Given that the blue jeans she's wearing probably took about 2,800 gallons, that pound of ground beef that she made for dinner is about 1,800 gallons. A cup of coffee took about 35 gallons of water to make. Again, this is total water usage for the product, not necessarily that she used 35 gallons to make a cup of coffee, right? 500 gallons for chicken, 400 gallons per egg use, right? Lots of water goes into the development of the stuff that we use in our everyday civilized lives. It is bonkers amounts of water usage. And you can see, look at these, how big these numbers are. 1,000 gallons for a car, 45,000 gallons for the beef that you ate. Stupid amounts of water, right? This water is not, sometimes this water is just being used up and going into the hydrologic cycle, so it needs to come down as rain at some point. Sometimes this water is being put back in the system, but very slowly, because aquifers will fill at the speed of, what I say earlier, an inch or two a year, something like that. Or no, inch or two a day, sorry. So the water takes a long time to get down the aquifers. We're using lots of water. It is ridiculous. Most residents of the Great Lakes states, around here, you never really had a water supply issue, right? Like, you look out your window, you can get on your bike and go to some of the largest freshwater lakes in the world. However, other places in the world do not have this benefit. As shown earlier, these aquifers, this Great Plains aquifer, is being depleted at a ridiculous rate. These people don't have access to water all the time. Well, if they do, they may have contaminations like we talked about earlier in the water. There's big issues with fracking going on, I think, in Virginia area, where the water is coming out brown and can be lit on fire. Usually, if your water can be lit on fire, it's not useful water, right? Lots of farming goes on around these aquifers that are basically drying up, and these rivers that are drying up. This is a bad problem, right? Sure, you can do dry land farming, which is a more natural way of going about it, but yields are lower, so you can use more land to farm it. Prices go up, etc., etc. Big issues. There are critical groundwater depletion issues in large swaths of the world. Critical surface water shortages as well. As I said before, damming up rivers. Just in general, not enough supply coming back to those rivers to filter through. And what happens when you do that? You get these anomalous looking pictures of essentially a huge amount of water flowing through a desert. Weird, right? In the 1920s, the average discharge of the Colorado River was about 18 billion cubic meters per year. Higher usual due to heavy rains. In 1922, the U.S. divided water usage equally between the upper and lower basin, naturally leaving nothing for Mexico. However, Mexico went like this. In the 40s, a new treaty was signed giving Mexico about a little under 2 billion cubic meters of water from the Colorado River. Sadly, precipitation never reached that of the 1920s, so the Colorado River does not have that much water to distribute to these different regions. And so what happens? Well, America soaks up a lot of this water, sometimes for useful things as agriculture, sometimes for ridiculous things such as palm tree covered water parks, causing issues. Mexico doesn't get that water anymore, right? That's an issue. Lots of places run out of water. Where are they going to get water from? This is a common issue we have to deal with. It's part of our day-to-day life. And at some point, us up here in the snow-covered water 10-minute bike ride away world might have to be dealing with that. So there you go. That is my presentation on groundwater. As usual, leave any comments down below, any questions you have, talk with your fellow classmates. Good luck on your homework, and I'll see you next time.